Alright guys, so we're continuing our focus in 6.4 on exponential growth and decay. And now we're going to start looking into modeling growth with other bases. And so, we've looked so many times into seeing the differential equation of dy dt. And so let's say we have dy dt, right? So there is the fact that this shows our exponential growth. And this leads to the exponential solution, alright, that y equals y naught times e to the kt, right? And so that's what we've been really focusing on so far. But, and we know as long as t is 0, y naught will be the value of y. But with that being said, we can actually use this formula for different bases because we can rewrite it, believe it or not, right? We can also write this solution in the form y equals y sub 0 or y naught times b to the h times t. Now let me explain our h and our t, or excuse me, our h and our b. And so b, okay, b is going to make sure that it's a positive number not equal to 1. So b is greater than 0, but b also does not equal 1. It's a positive number not equal to 1. And all h is, guys, is h is another rate constant, okay? H is another rate constant, okay? It has a relation to k. Its relation to k is the fact, alright, that k equals h times the natural log of b, okay? And so that's its relationship to k. So our original k, our constant of growth or decay, is equal to this new rate constant h times the natural log of b, which is just another positive number, very similar to how e is a positive number in there. All right. This means that the exponential growth can be modeled in any positive base not equaling to 1. All right, and it enables us to choose a convenient base to fit a given growth pattern. All right, and that's the big key, is that having this new formula, it allows us to find growth models not strapped down to using E as our base for every single thing. And so let's take a look at an example as to where we might see this. So it says, at the beginning of the summer, the population at the beginning of summer, the population of a hive of bald-faced hornets is growing at a rate proportional, that's key right there, guys, at a rate proportional to the population. From a population of 10 on May 1st, the number of hornets grows to 50 in 30 days. Ooh, giving us some information here. If the growth continues to follow the same model, in 30 days, getting to 50, how many days after May 1st will the population reach to 100? All right, well, the first thing to underline, rate proportional to the population, and it starts at 10 and ends with 50. That means that we know the growth is going to be exponential, right? Because it tells us, because it's proportionate, dy dt is equal to k times y. That's going to be the reason why it's growing proportionally to the population. Thus, it's going to have exponential growth, okay? Now, the population grows by a factor of what? Think about it. What's happening, right, in 30 days, right? From 10 to 50 in 30 days. Well, you gotta kind of think to yourself, it's really growing kind of by a factor of 5, right? Look by a factor of 5 in 30 days. And we model the growth in base 5. Now, we only need to solve the equation actually for t, right? And so in base 5, y will equal 10, your initial, times your base 5 to the 1 over 30 times t power. Because this is what happens, right? It's growing at a constant of 1 out of 30. Well, every single day out of those 30 days, it's growing at this rate. That's where we get our 1 out of 30 from, right? So 1 out of 30, the next day, 1 out of 30, the next day, 1 out of 30. Out of every single one of those days represents one day out of the 30 that it is having some kind of growth, okay? Well, now we got to think for ourselves is that we just need to simply find out, well, what happens when our population goes from 10 and then goes and ends up at 100. So really, y is going to be 100. 10 times our base 5 of 1 over 30 t, and then we just need to solve for t in the end. So dividing through by 10, we get 10 on the left-hand side, and we get 5 to the 1 over 30 times t. And then we want to go ahead and natural log both sides, so we can go ahead and get our t down below. And so we'll natural log, we will natural log, and this ends up giving us the natural log of 10 equals 1 over 30 times t. Once again, just using our logarithmic rules and properties of the natural log of 5. And then dividing through, or technically multiplying through, we'll see that in the end, t will equal 30 times the natural log of 10 over the natural log of 5. And simplifying this out in our calculator, we roughly get about 42.92 days. And so I would say, because it's 0.92, we could probably say roughly 43 days in the end. Okay? So, once again, think about possibly where we got some of this information from. All right, so we went from a population of 10 on the first, and then in 30 days, we grew 40, right? So in 30 days, we grew 40. So what's kind of happening, I guess, in those 30 days? Well, every day represents 1 out of the 30 that we're going to be doing, since we get our 1 out of 30 from. All right? So very interesting problems there. Very, very interesting problems that we're dealing with some of this information about change and growth and all that stuff as well, too. So I want to give one a shot on your own. Go ahead and try number 23, also going to be on page 357. Alright, I'm going to write it on down for us because it's all on there. Page 357, number 23. Alright, and on to the next one.